When observing a comb jelly, or ctenophore, it's easy to get distracted by the light show, but those rippling, alien-like rows of tiny cilia located all along its transparent body are actually a masterclass in fluid dynamics. Comb jellies operate at an intermediate microscopic scale, what physicists call intermediate Reynolds numbers. At this specific scale, water behaves like a thick syrup, where viscous drag and inertial forces constantly fight against any movement. This creates a major physical problem. If a microscopic organism waves a simple paddle symmetrically back and forth, it goes nowhere. Any fluid pushed forward on the power stroke is perfectly reversed on the backstroke, resulting in zero net movement. To generate forward thrust in this environment, an organism must break symmetry. It has to change both the shape and speed of its stroke between the outward push and the return sweep. Nature mastered this asymmetrical motion millions of years ago. But to prove exactly how these microscopic geometric shifts generate physical thrust, human engineers had to build soft robots of their own. To isolate the variables of microscopic propulsion, researchers cast bio-inspired artificial cilia out of a specialized magnetic silicone. This diagram shows three distinct propulsor shapes tested: flat, concave, and convex. Placed in a fluid tank under the exact same translating magnetic field, the robotic paddles bend, flex, and whip through the fluid in distinct ways based on their initial cast. By recording and comparing the water currents generated by these three shapes, scientists isolated the exact geometry required to overcome microscopic fluid drag. Look at the flat robotic paddle first. As it moves, fluid drag forces it to bend symmetrically during both the forward and backward strokes. This results in a near-reciprocal motion, the exact kind of movement that generates no net flow. On this horizontal velocity heat map, red is forward momentum and blue is backward flow. The bottom row shows the flat paddle's failure. Its recovery stroke pulls fluid backward, canceling thrust. The middle row's concave paddle performs better, but retains too much curvature. That lingering concave shape acts like a parachute, creating transient low-pressure pockets. Fluid gets sucked backward into that void, crippling the paddle's overall efficiency. If a paddle cannot drastically alter its physical profile between pushing water and returning to its starting position, it will endlessly fight its own wake. Panel D shows the biological winner, the concave paddle, achieving spatial asymmetry by changing shape mid-stroke. In the red power stroke, the paddle extends to maximize thrust. In the black recovery stroke, it bends tightly, slicing through water with minimal drag. It also masters temporal asymmetry. The convex shape executes a rapid, explosive power stroke, followed by a slower, drawn-out recovery. That intentional pause allows the moving fluid to coast forward without being disrupted by the paddle resetting itself. To multiply this thrust, comb jellies use metachronal coordination. Multiple asymmetric paddles beat in a sequential stadium wave pattern, known as an antiplectic wave, to ensure the fluid momentum never stalls. Mastering intermediate fluid dynamics requires a precise choreography of shape-shifting, speed-shifting, and sequential timing to transform chaotic drag into a continuous, unidirectional pump. Beyond these physical traits, Ctenophora actively computes and adjusts its fluid dynamics in real time. This diagram shows the statocyst, a sensory organ at the very top of the animal. Inside, a dense weight called a statolith rests against sensitive balancer cilia, acting as a gravity sensor. When the organism tilts in the water, the statolith shifts. This triggers a nerve net connected via ciliated furrows directly to the paddle rows. The jelly instantly adjusts its beat frequency, causing sudden stops or synchronized rebeats to perfectly reorient itself. This creature operates as a self-regulating feedback loop, where biological fluid dynamics are inseparable from the nervous systems that pilot them. Decoding the statocyst's control loop and the convex paddle's geometry provides a mechanical template for human engineering at the mesoscale. These geometric rules allow us to build untethered, bio-inspired swimming robots capable of navigating complex aquatic environments without relying on bulky motors. This mechanism of asymmetric beating can be applied to design targeted, microscopic pumps that safely move fluids or deliver drugs within the human body. Conquering the physics of the microscopic world relies on the mesmerizing asymmetrical rhythm used by one of the ocean's oldest inhabitants.